Okay, we proceed with Module 5, which covers Introduction to Probability, wherein we're going to recall some of the basic terms and concepts, and also some basic relationships of probability. Okay, and nothing in life is certain. There's always that sense of uncertainty in every aspect of our lives. That's why we gauge in the chances of successful outcomes, may it be in the field of business, medicine, or even in the field of weather, for example, and other everyday situations, such as, let's say, you bet in the lottery. And we look at probability as a numerical measure of the likelihood of occurrence. So we keep in mind that the range of values of a probability of a certain event will be within 0 and 1. That means to say we cannot have negative values for our probability in the same manner that we could not have probability values which are more than 1. Okay, so if the probability of an event is close to 0, then we say that the event is very unlikely to occur. And in the same manner, if the probability value of a certain event is close to 1, then the event is almost certain to occur. Okay, however, if the value of the probability of a certain event is zero point 0.5, then we say that the occurrence of the event is just as likely as it is unlikely to occur. Okay, so we will look at the range of values later on in terms of the kinds of events involved. If the probability is equal to 0, and also when the probability of a certain event is equal to 1. Okay. And here, there are three approaches to probability. So we will go over them one by one. So we have what we call the classical probability, or also known as theoretical probability, which is used when each outcome in a sample space, okay, when we talk of the sample space, it is a set that will contain all of the possible outcomes, okay, is equally likely to occur. And the classical probability for an event E is given by the following notation. So we will make use of this notation to indicate that we are referring to the probability of event E occurring. And the probability that an event E is going to happen is equal to the number of outcomes in event E, or we say the number of successes in event E, and we divide it with the total number of outcomes, okay, in sample space. And let's take this for example. Say a die is rolled, and we would want to find the probability of event A, wherein event A is the event that we roll a 5. So we recall that a die has 6 faces, and each face is numbered with 1, 2, 3, 4, 5, and 6. So in this case, we are looking for the probability of the event that a 5 will turn up when you roll a die. And here, there is only one outcome in event A. That is because there's only one phase with a number 5. Alright? So therefore, the probability of event A occurring is that there's only one outcome in event A of rolling a 5 out of the total 6 outcomes, okay, in the experiment of rolling a die. Why 6? It's because there are 6 faces in a die. Okay? And we'll proceed with the second approach, or what we refer to as the relative frequency approach, also known as empirical probability, or empirical or statistical probability, which is actually based on observations obtained from probability experiments. So here, the empirical frequency of an event is the relative frequency of the event E. So let's take, for example, probability of an event E to occur is equal to the frequency of event E. We divide it by the total frequency. That means to say it is the number of times of event E occurring, and we divide it by the total number of times that the experiment was performed. And in this case, let's take this for example. Say a travel agent determines that in every 50 reservations she makes, 12 will be for a cruise. Okay, so meaning to say, the experiment involved is having to make a reservation, and she performed the experiment 50 times by having to make 50 reservations. And the frequency that, or the frequency of an event that a cruise is chosen, or a reservation for a cruise was made was uh, 12 times. Okay, so in this case, we are interested with the probability that the next reservation she makes will be for a cruise is given by the probability that a cruise reservation was made will be equal to 12 times out of the 50 reservations that the travel agent made. And in this case, it will be equal to 6 over 25 in simplest form and equivalent to 0.24 or 0.24 in decimal value. So in this case, you may express your answer in fractional value or in simplest form, or it could be in a decimal value. Okay. And another way of also writing or presenting your answer is by the use of percent. Okay, so that means to say if the probability value of an event will range from 0 to 1, the equivalent of that in percent would be from 0% to 100%. So mean to say you cannot exceed 100%, indicating that you cannot have a probability which is more than 100%. In the same manner, you can't have a probability which is less than 0%. Okay, so let's proceed with the third approach to probability. Or in this case, before we do that, let's have another example. Here, we're presented with a table, and the following is a frequency distribution that represents the ages of 30 students in a statistics class. And we are interested with the probability that a student is chosen is between 26 and 33 years old. So if you notice here, for the age group na 26 to 33 years old, there's a frequency of 8. There are 8 students belonging in this age group. And we take note that the total frequency is equal to 30 because there are 30 students. So all you have to do is add all of these frequencies. And computing for the probability that a student is between 26 and 33 years old is there are 8 of them. Okay, so we have 8 out of 30. And in simplest form, that's equivalent to 4 over 15. And double check the value in decimal, it will be equal to 0.2667. So in this case, I'm making use of up to 4 decimal places. Okay, and we'll proceed with our third approach to frequency, or third approach to probability. We have what we call the subjective probability, and this results from intuition or an educated guess and estimates. And let's take the following example. So say a business analyst predicts that the probability of a certain union going on strike is 0.15. So this is an example of a subjective probability. It's because this claim, okay, or this statement is a result of an educated guess or simply an estimate of the business analyst. So basically, in this case, no computations were done. Okay, so recalling the range of probabilities of a certain event, it will range between 0 and 1 inclusive, meaning it could be equal to 0, it could be equal to 1. That is, the probability of an event A occurring would be within 0 and 1. And in the case that the probability is equal to 1, then that means to say the event is impossible to happen. Thus, we have what we call an impossible event, the moment the probability value is equal to 0. Similarly, when the probability is equal to 1, then we have what we call a certain event or a sure event because we are certain that it's going to happen. Alright? And also, if the probability is halfway between 0 and 1, or that is equal to 0.5, then we have an even chance that the event is going to occur and the event is not going to happen. So we have 50% chance it's going to occur and 50% chance it may not occur. Okay? Now, we will need to recall some of the set operations you've encountered in algebra or in set theory. Okay, so we'll go over them one by one. That's because they are the concepts there are used in the concept of probability. So let's recall what we refer to as the complement. But in this case, we are talking about complementary events. So the complement of event E, okay, is the set of all outcomes in the sample space. Okay, remember the sample space is the set that contains all of the outcomes that are not included in event E, which we denote by E prime or the apostrophe. Or in some reference materials, they make use of E to the C. They use a superscript of C here, okay, which is read as E prime. Or in that case, we are referring to the complement of event E. So it is the set of all outcomes that are in the sample space or synonymous to our concept of universal set. Okay, however, those are not in event E. Okay, let's have the following equations relating the complement of an event. So here we say that the probability of an event and its complement, or the probability of its complement, will sum up to 1. Okay, so that means to say if we know the probability of its complement and we're looking for the probability of event E, so we simply subtract the probability of its complement from 1. Okay, in the same manner, if we know the probability of an event E, we subtract it from 1 to get the probability of its complement. That's because the probability of our sample space, okay, is equal to 1. That means to say everything, or the sum of all probabilities in your sample space, is equal to 1. Alright? Let's have the following example. Say there are 5 red chips, 4 blue, and 6 white chips in a basket. So we are asked to find the probability of randomly selecting a chip that is not blue. Okay, but what we're given are 5 red, 4 blue, and 6 white chips. So in this case, let's say, for example, I'm going to find the probability of selecting a blue chip. And I know that in the given, the total number of chips in the basket is composed of 5 red, 4 blue, and 6 white. Okay, so we have 4 blue chips out of the total number of chips inside the basket. Thus, our probability would be 4 blue chips out of the 15 that are inside the basket. Okay, and since we're looking for the probability of selecting a chip that is not blue, okay, so I will use this knowledge that the probability of selecting a blue chip is 4 over 15. From what we have here, we are looking for the probability of the complement of our event E. That is, in this case, a probability of not selecting a blue chip. So with our formula, we subtract from 1 the probability that we are able to select a blue chip. And the probability of selecting a blue chip is given by 4 over 15. So subtracting that from 1, we get 11 over 15. Okay, or in decimal value, that would be equivalent to 0.7333. Okay. Or another way of looking at the problem, if you notice, the colors of the chips inside the basket are red, blue, and white. So when we talk of, or by common sense, okay, if you are asked of the probability of selecting a chip that is not blue, then meaning to say, you may possibly be able to select red, okay, or white chips. And the total number of red and white chips in the basket would be 5 plus 6 is equal to 11. So that would be 11 chips that are not blue, okay, out of the 15. So you will end up with the same answer. Okay, so I hope you were able to look at that problem in that different perspective, or in a different view. Okay, okay, let's continue. Now, we will need to recall some of these concepts, the complement of an event, when we talk of the union intersection, and we are going to introduce what we refer to as mutually exclusive events. Okay? And let's proceed with what we refer to as a complement of an event, as how it was presented to you in algebra or in set theory. So when we talk of the complement of an event, we say the complement of event A is defined to be the event consisting of all sample points that are not in A. Okay, so when we talk of sample points, or in this case, outcomes, okay, or elements inside the box, okay, or inside our sample space. So the rectangular box that we have here would represent our sample space, which we will denote as S, okay? And we will take this circle inside the rectangular box as our event A. So when you talk of the complement of event A, we are referring to all of the elements that are inside the box. However, are not contained in the circle which we have denoted as our event A. So that means to say it will be the blue region. And this blue region is denoted by our complement of event A, or that is indicated by A prime or A C, okay, or A to the C, indicating the complement of event A. So recall that in algebra or in set theory, we refer to this illustration as a Venn diagram. So we will see later on in some of probability problems that we may encounter, having to visualize it using a Venn diagram may be helpful. Okay? Now let's continue. Let's proceed with the concept of the union of two events. So we say the union of events A and B is the event containing all of the elements or all outcomes or sample points that are in A, take note, or in B, or both of them. Okay? So this is denoted by the following symbol that we have here to indicate the union. Okay, so we say the union of events A and B is denoted by A union B. So if this is your event A and this is event B, by definition, we are talking of all elements that are in A, so everything in A, okay, or in B, okay, or found in both of them, so in this region. So basically, when we talk of the union of events A and B, it will be everything inside the two circles. Okay, so we combine all of the elements or all of the outcomes in the two events. We are talking of the union of these two events, which can be extended to more than two events. You can take union of three or four or even more than three events involved. Okay. Now let's continue with what we refer to as the intersection of two events. Now, when we say intersection of events A and B, it refers to the set of all sample points or outcomes that are in both A and B. So take note of our clue word here. Both A and B. So the intersection of events A and B is denoted by this notation. Okay, so it's just the inverted notation as what we've indicated in the union of two sets or two events earlier. So in this case, if this is event A and this is event B, the intersection of A and B is represented in the region where the two circles actually would overlap. Okay, so this contains all outcomes or elements that are found in event A, okay, and B at the same time, common to both of them. Okay? Now let's recall, or in this case, we have what we refer to as the addition law. Right. So here, with the addition law, this provides a way to compute the probability of event A, all right, or B, or both A and B occurring, which is in symbol is denoted by the probability of A, okay, or B occurring. And that is given by having to take the probability of event A plus the probability of event B, and we subtract the probability of the intersection of the two events involved. Okay? If in that case here, we will just go back to the addition law later on. Okay? So we are going to introduce another concept or what we refer to as mutually exclusive events. Okay? So here the two events are said to be mutually exclusive if the events have no sample points or elements or outcomes in common. The two events are said to be mutually exclusive if when one event occurs, the other cannot occur. Okay, so we need to say the two cannot occur at the same time or together. So we have event A here and event B. Okay, so they are mutually exclusive events. They don't have any common outcomes. That's why they do not overlap. Because the moment they overlap, the overlapping region indicates or includes the common outcomes found in both of them. But since they are mutually exclusive events, so the two events do not overlap in our illustration or in our Venn diagram, that's because it have no sample points or no outcomes in common. Okay? All right. Now, here, with our addition rule or addition law that was presented earlier, okay, so the addition law for mutually exclusive events will be given by the following. That's because since when the events are said to be mutually exclusive, since they do not overlap, it will indicate that their intersection is equal to zero, or the probability of their intersection will be equal to zero. Thus, going back to our addition law for for what we have presented earlier, probability of A union B is equal to probability of A plus probability of B minus the probability of their intersection. But since they are mutually exclusive, okay, and that is equal to zero, we do not have that here anymore. So when the two events are mutually exclusive, and finding the union, the probability of their union, we simply have to add their individual probabilities. So we simply add the probability of event A and the probability of event B. Okay? Now, here, so let's elaborate on it further. So two events A and B are said to be mutually exclusive if they cannot occur at the same time, right? So here in this illustration, these two events A and B are mutually exclusive. They don't have anything in common. They do not overlap. Okay, however, in this case, A and B here are not mutually exclusive. That's because the two of them overlap, and this region indicates outcomes that are common to both of them. Okay? Let's have the following examples. Let's identify if the events involved are mutually exclusive or if they're not. So say here we decide if the two events are mutually exclusive. We have event A. Event A is that we're going to roll a number less than 3 on a die. So again, a die has 6 faces with numbers 1 up to 6. So for event A, rolling a number less than 3, okay, would yield faces with numbers 1 and 2. That is for our event A. What about for event B? Event B is that we roll a 4 on a die. So therefore, event B will only contain one outcome because in a die, there's only one face which is numbered 4. Okay, so looking at our event A and B, they don't have anything in common. Okay, thus we say the events cannot happen at the same time, so the events are mutually exclusive. Okay, like let's have another example. Say event A is the event of selecting a jack from a deck of cards, and event B is selecting a heart from a deck of cards. Okay, so if we're going to illustrate event A, wherein we are selecting a jack from a deck of cards, there are four cards with different suits that are jack. Okay, so recalling a deck of playing cards, we have numbered cards from 2 to 10. Okay, we have ace, then we also have jack, queen, and king. And for each of those cards, okay, we have a um, a card which is a diamond, a heart, a club, or spades. So there are four of each kind. Thus, we have 4 times 13, we end up with 52 cards. So we keep that in mind. Okay? So going back to our example, event A is selecting a jack from a deck of cards. So we will have 4 of them. And event B is selecting a heart from a deck of cards. So since selecting a heart from a deck of cards would mean to say that we will get an ace of heart. Okay? Um, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then we have jack, queen, and king. All right, and notice that the jack of hearts, okay, is found in both A and B. All right, they have something in common. So meaning to say we're able to find an outcome common to both of the events that we have here, meaning to say it can occur at the same time. So therefore, we say that these two events are not mutually exclusive because the card can be a jack and a heart at the same time. So the events are said to be not mutually exclusive. Okay, I hope this is clear. All right. Going back to our addition rule, let's expound on it. So the probability that event A, take note, or B will occur is given by the following. That is probability of A or B, or this is indicated by the union, okay, notation, is equal to the sum of their individual probabilities, and we subtract the probability of their intersection. So in symbols, we have the probability of A union B is equal to the probability of A plus probability of B minus the probability of A intersection B. Okay, so if the events A and B are mutually exclusive, however, then the rule can be simplified to simply getting the sum of their individual probabilities. It's because when they are mutually exclusive, this probability of the intersection will be equal to 0 because it's impossible for them to occur at the same time if the events are said to be mutually exclusive. Alright? And let's go back to the example that we have presented earlier. So we say you roll a die. We find the probability that you roll a number less than 3 or a 4. As what we have indicated earlier, these two events are said to be mutually exclusive because we could not find a die which is less than 3 and equal to 4 at the same time. Okay? Or thus, the probability that you roll a number less than 3 or you roll a 4 is given by having to get the probability that a number is less than 3 plus the probability that you get a 4. Okay? And the probability that you get a number less than 3 as what we have presented, that will be a face of the die with numbers 2 and 1. So that will be 2 out of the 6 faces plus the probability that you get a face which is numbered 4, and there's only one. That is 1 out of the 6 faces. So we end up with 3 over 6, which is equal to 1 half, and that is equal to 0.5. Okay? Right. Let's have another example. The second example we have presented earlier. Say a card is randomly selected from a deck of cards, and we are asked to find the probability that the card is a jack or the card is a heart. As what we have pointed out earlier, these two events are not mutually exclusive because we're able to find the jack of hearts having to occur in both events. Okay? Thus, the probability of selecting a jack or a heart is that we get the probability that we are able to select a jack plus the probability that we're able to choose a card which is hearts, okay, minus the probability of getting jack of hearts. So how many jack cards are there in our deck? There will be 4 out of 52 of them. How many hearts? Okay, how many cards wherein the suit is a heart in our deck of cards? There will be 13 of them, one of each kind, out of the 52. Minus, how many jack of hearts are there? There's only one jack of hearts out of the 52. So simplifying this, we come up with 16 over 52, or that will be equal to 4 over 13 in simplest or in lowest form. Okay, in decimal, that is estimated to be equal to 0.3077. Okay, so I hope this is clear. Right? So you will know that you will use the addition rule. Okay, take note. The moment in the question you are asked to find the probability of an event, or, well, that's your clue word there, or you are asked of the occurrence of another event. So if you have an or there, that means to say we can make use of the addition rule. But keep in mind, if the events involved are mutually exclusive or not. The moment they are not mutually exclusive events, this is the formula that you're going to use. If they are mutually exclusive events, then that means to say you simply have to add their individual probabilities. That's because the probability that both are occurring at the same time will be equal to 0 the moment the events are said to be mutually exclusive. Okay? Now, let's have another example. Say our data is presented in tabular form. Say we have 100 college students that were surveyed and asked how many hours a week they spent studying. The results are in the table below. And we are asked to find the probability that a student spends between 5 to 10 hours or, so take note, or more than 10 hours studying. So we're interested with the event that the student spends between 5 to 10. Okay, so it will be this column, okay, or more than 10 hours studying. Okay, now, may I ask you, if a student is spending between 5 to 10 hours studying, okay, can that student be spending more than 10 hours studying at the same time? Okay, in that case, they are mutually exclusive events. That's because the moment the student is spending between 5 to 10 hours studying, then that means to say he or she is going to belong in this category. Thus, he or she could not belong in this category, which indicates of studying more than 10 hours. In the same manner, if the student is studying more than 10 hours, then he or she could not belong to 5 to 10 hours na category. Okay, so therefore they are said to be mutually exclusive events. So if they're mutually exclusive events, we simply have to get their individual probabilities, just add them. Thus, the probability that a student spends 5 to 10 hours or more than 10 hours is given by the following notation. So probability of 5 to 10 union with more than 10. Since they are mutually exclusive, we simply have to add their individual probabilities. So we will look at the table. What is the probability that a student is spending 5 to 10 hours? Okay, plus the probability of more than 10 hours. So in this case here, we look at the column for 5 to 10, and the total there is 46. Okay, out of the 100 students. So mean to say, out of the 100 students, 46 of them are studying from 5 to 10 hours. In the same manner, for more than 10, there are 30 of them out of the 100. Therefore, we have 46 out of the 100 who are studying 5 to 10 hours. And the probability that the student is studying more than 10 hours is that there are 30 of them out of the 100. Therefore, we have 30 over 100. So simplifying this, we get 46 plus 30 will give us 76 over 100, or that is equivalent to 0.76. Okay, I hope this is clear.